Hey, I wanted to record a video on going through the assignment, so I will do that. So determine which of these three devices is best described as a DC motor, a DC generator, and an AC generator. Okay, so you can see we have the single ring here, which is a split. Keep money. Hello, hello, hello. Oh, sorry, I thought my sound cut out. Okay, I think it's still working. So we have a single ring, which is a split ring, which means it's DC. So these 2 and 3 are DC, and you have a battery hooked up to this. So a battery is what you'd have on a motor. So device 2 is a motor, but a DC motor. This is a DC generator because it has like a dial on it that shows how much current is being produced. So you're generating the current, and this has the same dial. So this is a generator. That's an AC generator because it's got 2 of them. It's got the slip rings. So note the key parts of the device and choose from the following each part. So the rotating coil. It looks like rotating coil. Yeah. F would be the rotating coil. The brush, it's maybe H. I don't know why they don't do it in the same diagram. The slip rings is definitely B. Split ring commutator is F. I don't know. F and H. The voltmeter would be what they're measuring the current or voltage on, so that would be C. Voltage source would be G, and then your permanent magnet would be D. So, yeah. Oh, rotating coil. Sorry, I actually had that wrong. The rotating coil is A. That's the coil that rotates in the magnetic field. Sorry, that was my bad. Okay, and I think the brush is actually B. And the slip rings are E. Sorry. Yeah, diagram's not great. Okay, but the first question is more important anyway, identifying which one is AC, DC, which one is a motor and a generator. And then 3, draw a voltage versus time graph for AC, DC. So voltage versus time for AC would be like that, and voltage versus time for DC would be like that. And what are advantages to AC over DC? Well, AC can transmit longer distances, it can use transformers, and it's more efficient. It's a more efficient way of generating electricity because you don't have that split ring commutator that causes a lot of friction. Okay, so hopefully that helps, and let me know if you have any questions.
Hey, Science 30s. So we're going to start off with some sample diploma questions from that stuff we did last lesson. So we'll start off with this one. So make sure to give these a go on your own before me going through them. So which of the following rows contains a statement that should be placed in area 1 and a statement that should be placed in area 3? So area 1 just relates to alternating current. So which one only relates to alternating current? So batteries, they are direct current. So that eliminates A and B. Using a transformer is just alternating current. And something that relates to both, well, you can make a motor out of both, as they showed in that video. So D would be the correct answer. Number 10, the purpose of the motor shown above is to convert electrical energy. So motor, you want to make motion, so you want to convert electrical into kinetic. And you can see there's a split ring commutator, which shows us that this is a DC motor. Okay, and this one here, the generator below is similar to one that would be in a coal-fired generating plant. And giveaway here, slip rings. So as soon as you see slip rings, you know that it has to be AC. And if it's AC, the voltage is going to vary over time. So that gives us A is the correct answer. Okay, and then this last one here. The coil of wire is rotated in a magnetic field of a U-shaped magnet. The current is generated in the coil and measured by the ammeter. So the above illustrates the process of, so when you use motion, which they're using motion to create current. We call that induction. So you induce a current. That's what's happening in this situation. And again, you can see this split ring commutator. So this is a DC setup here, and this is a DC generator. Okay. So today we're going to talk about circuits. Yeah. So we're going to use some formulas shown here. We're going to calculate resistance in parallel and series. We're going to calculate values for power, current, voltage, and resistance. And we're going to describe in terms of design and electrical energy the functioning of safety technologies. So circuit diagrams, so these are circuits like building batteries, building motors, things like that. Circuit diagrams or schematics are representation of a circuit that's built. So if you want to build a circuit, you need these things. You need a source that provides the energy. You need a conductor that provides a path for the current. So you need the wire. So this one would be a battery, or you can plug it in. A switching mechanism that can turn the power on and off. So a switch, and a load that converts electrical energy in some other form. So you want to put a light bulb or a motor or something. There has to be a goal with your circuit. You don't just hook a battery up to wires and then have the battery run out. Okay, so these are different symbols that you need to know. So this is a wire. This is a switch here. This is a power supply. So one thing that we use in everyday life incorrectly is the term battery or cell. If you're thinking about like an individual battery, so without the spikes, oh man, I'm trying to draw a battery here. There we go. So this is what we call a battery, like a AA battery, but technically that's a cell. So it doesn't become a battery until you stack another battery on it. So when you have two or more batteries together, two more cells together, you make a battery. So a battery is two or more cells, and then this is just one cell. This is a resistor, a light bulb, voltmeter, ammeter, ohm meter. And the only other one that's not on here that you need to know is sometimes you'll see an AC power source. So this is what an AC power source will look like. So sometimes you'll see that, and that's what it is. Okay, so this is an example. So here we have two cells. So we'd have two everyday language batteries. We have a switch, and we have a light bulb, and then this is the wire here. So there's two types of circuits. So there's parallel, and then there's series circuits. So these types of circuits are defined by the number of branches that are present. So this is a series, and the reason that it's a series is because there's only one pathway. Actually, the electricity goes the other way. It goes from negative to positive. Anyways, but there's only one path for it to go through. So we'll start with the series circuit. So series circuits are when current passes through each bulb in turn. There's only one pathway for the current. So the current has to go through this wire, it has to go through this bulb, it has to go through this bulb, and then, yeah. So if you add more bulbs, it increases the resistance, making the bulbs dimmer. So if I threw another bulb in here, all the bulbs would become dimmer. So a light switch in a house would be wired in a series because one light switch can turn off all the lights in your living room. So that's how you'd want it to be wired. So parallel circuits have a separate path for each section, right? So the current has a couple options. It can go this route, or it can go this route, right? And if this bulb burns out, well, it can still make it through this bulb just fine, as opposed to if this bulb burns out, well, all of a sudden you have a block in the path and all the bulbs would burn out. So if you interrupt a circuit, it doesn't affect the other parts of the circuit, right? And adding extra circuits, so adding on another light bulb here, actually lowers the resistance because it gives more pathways to go through, right? You can sort of think of it like traffic. So if you have a series circuit, it's kind of like cars can only go through one road, right? So if you add more things in here, it's more congestion for all the cars to go through. But this is a road and there's multiple paths that cars can take. So if you add another path that cars can take, it actually lowers the congestion, lowers the resistance, and would make the light bulbs brighter. So parallel circuits are more commonly used than series circuits, right? If you look at this house here with all these light bulbs, imagine what your house would be like if it was wired in series. So if one of these light bulbs burnt out, every single light bulb would burn out, which would be frustrating. And you wouldn't know which one would burn out, so you'd have to test all the light bulbs in your house. So most of the circuits in our house are wired in parallel to avoid this problem. Okay, so we're not really going to get a chance to use these in person, but I do have a little online lab that you can do. So voltmeters measure voltage and must be connected on either side of the device, so they must be connected in parallel. So if I wanted to measure the voltage of this circuit down here, I have to connect my voltmeter in parallel, meaning I have to give my voltmeter its own little circuit. And I have to do it on either opposite side of the battery, or I'd have to set it up on opposite sides of the load. We need a difference between one side to the other. If I set up a voltmeter here, it's not going to do anything because there's no difference between these sides. So you can see I've set it up in parallel because it has its own circuit. Ammeters measure current, and they show the same reading at any point, and they have to be set up in series. So if I set up my ammeter, I just want to make it like a light bulb. I want to make it part of my circuit, and I can set it up anywhere that I want. A galvanometer just measures small current, so you might see that term used, and a multimeter can measure voltage, current, or resistance. So this is what you'd use in your home. So show how you would hook up a voltmeter and an ammeter to a battery with two bulbs, to a circuit with two bulbs in series and a battery. Okay, so if we want to draw a battery, it would look like that. That's one cell. So if we want a battery, we need more than one cell. Okay, and we can have a light bulb here, and we can have a light bulb here, and we can have a switch if we want. Turn it on and off, and it would look like that. Okay, so if I wanted to set up a voltmeter, I could set up a voltmeter to measure my voltage across one of them, or I could measure across both of them if I wanted, but it has to be set up in parallel. That's the most important part. And if I have an ammeter, I want it to be set up in series, so I can put it anywhere along that circuit. So a fuse or a breaker, if it receives too much current, the circuit is broken and it stops. So this is what fuses look like. Fuses all work on the same idea. They all have a wire in here, and when current goes through a wire, it heats up. So these are special types of wires that when they heat up, they burn up. So if too much current passes through here, this will burn up and it'll stop the current from flowing across there, so you don't start a fire. So all these are the same sort of way. This is a breaker, which is a lot more complicated, and this is what you'd have in your house. When too much current goes across the breaker, it trips, but it allows you to reset it. So that's the nice thing about breakers. Fuses, you have to replace them like in a car if they burn out, but breakers, you can reset them and you can use them over and over again. So resistors are part of the circuit that provides high resistance to reduce the amount of current flowing through the circuit. So this little picture here shows a really good image of what everything does in a circuit. So the voltage pushes everything along. Without a voltage, nothing would happen. So it gives it that push. Current is the electrons flowing through the wire, and then your resistance, which is measured in ohms, that's why it's here, sort of tries to strangle that off and doesn't allow current to flow through like it would want to. So resistance is a measure of how difficult it is for electrons to flow, and resistance is measured in ohms, which has this symbol here, which is looks like a Lululemon symbol. It's omega. It's a Greek letter. Yeah, so that's how we write resistance. So switches in a circuit can create a break in the circuit that interrupt the flow. But instead of just on and off, what you can have is you can have something called a variable resistor. So variable resistors allow you to control, you can up the resistance, lower the resistance to change the amount of current. So this is how basic dimmer switches work, or like the knobs on your stove would do that as well. They allow you to change the amount of resistance that go through there. So these resistors, known as rheostats, allow you to adjust the amount of current flowing through a circuit rather than simply turning it on and off. So factors that affect resistance, the temperature affects it. So as temperature increases, so does your resistance, which is bad because resistance causes heat. So as it gets hotter, it increases the resistance, which increases the heat, which would make it hotter and hotter and hotter. And this is why your phone will shut off if it gets too hot, because it doesn't want it to overheat. So for resistors to work best, they have to be kept cool. That's why computers have fans and things on it. And a thicker, shorter wire has less resistance. So if your car battery is a DC battery, all batteries are DC. So if you look at the wires in your car, they're really, really thick, and that allows for less resistance because DC has a lot of resistance, as we saw in that video. Voltage is a measure of how much potential energy each electron that flows through the circuit possesses. The reason I have this here is because this is a definition you'll see on a test. I don't love the definition, but sometimes they ask questions about this definition. What is voltage? And this is the definition that you need to know. And voltage is related to both current and resistance. And this is Ohm's law, V equals IR. This is how we can calculate voltage, current, or resistance if we have two of the other ones. Okay, so voltage is in volts. Current, which has a symbol I, is in amps. And then resistance, which is R, is found in ohms. So those are the units. So ohms, amps, and volts. So we'll do some questions with it. So a stove is connected to a 240 volt outlet. If the current flowing through the stove is 20 amps, what is the resistance in the heating element? So we'll use Ohm's law, V equals IR. And we are trying to find resistance. So it's important that you find what are you trying to find? V equals IR. So we're trying to find resistance. They give us current. They give us voltage. So all we have to do to rearrange this equation is we can move the I down below here. We can move that diagonally. We want to go voltage divided by current equals resistance. So 240 volts divided by 20 amps. And that's going to be our resistance. So you can do that in your head. So that's going to be 12 ohms. Okay. A 12 volt battery runs through a 15 ohm resistor. What is the current produced? So again, we use the same formula. V equals IR. It says what is the current? So we're trying to find I. So to rearrange this formula, we move R down below, and we would just go 12 volts divided by 15 ohms. And maybe we can't do this one in our head, but if we go 12 divided by 15, we get 0.8 amps as our answer. Okay. So that's what you did in grade 9. So that's really easy. But we're going to step it up a little bit. We're going to calculate total resistance in series. So for resistors in series, there's only one path for electricity to flow, and the current has to overcome the resistance of every bulb as it goes through the circuit. So we can use this formula here to calculate resistance in series. Okay. Yeah, so I'll talk about it when we do it. So this is resistance total, and this is, well, this Rn means we can have as many resistors. We can have 1, we can have 2, we can have 3, we can have 20. We just add them all together. If we're doing it in parallel, there's multiple paths, and like I said, the more resistors in parallel we add on, the more paths electricity can move. So this makes the current flow more easily and actually reduces the resistance. So to calculate total resistance in parallel, we got to use this formula which is a little bit more complicated. We'll do an example. So all these formulas that I showed you, they can be found in your data book. So if we open up our data book to page 3, we can see Ohm's law. V equals IR is there, and then the total resistance in parallel, total resistance in series, and it gives a little explanation of all the different things, what they mean, what the units are. So you have that in your data book. Okay, so let's do an example. A set of Christmas lights is wired in series. A string has 8 bulbs, each with 64 ohms of resistance. We're going to draw a schematic diagram, and we're going to find the resistance across the entire string. Okay, so those are the first 2 steps that we're going to do. Okay, so I'm going to do it on the whiteboard here. So if we drew a schematic diagram, a Christmas light is wired in series, and the string has 8 bulbs. So we need a power source. The power source for Christmas lights would be an AC power source. So we can draw our power source like that. And we have 1, 2, 3, 4, 5, 6, 7, 8. And most Christmas lights don't have a switch, so we don't need to include a switch into there. That's what our schematic diagram would look like. So find the resistance across the entire string. Well, it told us that each bulb is 64 ohms. So to find the resistance total, we just have to go resistance 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8, which is a little bit ridiculous. I should have made this smaller. So we just have to go 64 plus 64 plus 64 plus 64, and we just have to do that 8 times. So if I just go 64 plus 64 plus, oops, I'm going times. 64 plus 64, 3, 4, 5, 6, 7, 8. I can find my total resistance, which is 512 ohms. Okay. Or you could just go, I don't know, some of you are probably saying, why is he doing it like that? You can just go 64 times 8 because there's 8 of them and you get 512 as well. Okay, so there's a second part to this question. It says, if the lights are plugged into a 124 volt outlet, calculate the current that will flow through it. So we need to use that total resistance. This is our resistance total. And we can use Ohm's law along with that. V equals IR. So if we want to find the current, we can move our resistance down below, and that's going to be our resistance total. So it said it's a 120 volt outlet. Our resistance total is 512 volts. So if we go 120 divided by 512, then we get the current across there to be 0.23 amps. Okay, and that's how you do series, which is super easy. Parallel is a little bit trickier. So let's do an example with parallel. So during a dance, students set up 5 spotlights wired in parallel. Each light has a resistance of 96 ohms. They are hooked up to a 240 volt outlet. So why is it a good idea for the lights to be in parallel? Well, you can think about it for a sec, but I'll just tell you the answer. When you're doing a dance, you want the lights to sort of turn on and off all at separate times. So if you didn't hook them up in parallel, you'd either have all 5 lights on or all 5 lights off. So you'd have blinding light or no light, which wouldn't make a very good dance. So what we're going to do is we're going to draw a schematic diagram, and we're going to find the total resistance. Okay. So we have 5 lights, and they're in parallel. So again, it's an AC hookup because we're plugging it into the wall. So we have to draw each lamp on its own circuit. So we draw it like this. So that's what our schematic diagram would look like, which is much different than a series. So to calculate the resistance total, this is a formula that we have to use. Okay, so I would have to go 1 over, and it says that each one has 96 ohms resistance. So 1 over 96 plus 1 over 96 plus 1 over 96 plus 1 over 96 plus 1 over 96. 5 times. Okay, so I'll show you a nice way of calculating that in your calculator. Is you can just, instead of going 1 over, you can just go 96 and then push this button here, which goes to the -1. 96 to the -1 is the same thing as 1 over 96. So we just do that 5 times. Right? And we get that. And a lot of people would give that as our answer. But if we go back to our screen here, so what was that answer? So 0.052. So this is 0.052. But that's not resistance total. That is 1 over resistance total. Right? So what we need to do is we can move resistance total diagonally up here, and we can move this down here. So we get 1 over 0.052 equals our resistance total. So we need to inverse that number again. We need to 1 over that number. So this answer is never going to be our answer. We need to take this answer and we need to 1 over it. And when we 1 over it, then we get the right answer. So our resistance total is equal to 19.2 ohms, which you can see is less than the individual ones. Okay, and then if we want to finish off the question, it says, what is the current required to power all 5 lights? So same sort of thing, we can use Ohm's law. So we can use V equals IR, and we're trying to find current. So voltage divided by resistance. In the question, they told us that it was a 240 volt outlet. The resistance is 19.2 ohms. So if we type that into our calculator, just go 240 divided by that 19.2, we get 12.5 amps as our final answer. So each bulb gets 12.5 amps. Okay, that's what you need to know how to do this lesson. I will post an assignment to go with it, and yeah, that is all.